Welcome to lecture number 60. We will continue studying three-phase systems, and in this lecture we will study delta connected source, where the source is a three-phase delta connected system and Y is connected in the form of a Y. So it's a Y connected load and a delta connected source, and we'll study how to tackle with this situation. We are given all the line voltages. These are line voltages from A to B, B to C and C to A. 208 at an angle of 0, at an angle of minus 20 and at an angle of minus 240. These are line impedances, the line that contains the signal or the voltage from the source to the load. So the line impedance is the same per phase for each line, and the load is a delta connected, it's not delta connected, it's star connected load, and we are asked to find, in this situation we are asked to find VAB. VAB, we know it's a line voltage, and since it is capital A and capital B, this means it is on the load side. So on the load side we have to find this line voltage, right? So to make calculations easier, we generally convert into one system. Either we convert this into a delta connected load, or we convert the source into a Y connected source. To make per phase calculations, it is easier to convert this delta connected source into Y connected source, and we know that when we convert it, it becomes I have made a calculation for that. It becomes 120, because 208 when converted into phase voltage, we know the line voltage VL is under root 3 times V peak, V phase. So since this is line voltage, we are going to convert it into a Y connected system. So therefore this whole would be replaced with a Y with 3 sources, right? So this VAN, if this is A, this is terminal C, this is terminal B. VBN and VCN would be the phase voltages instead of line voltage, and the value would be under root 3 times smaller. So V phase is VL over square root of 3. So if we put 208 here, divide by square root of 3, it gives us 120 volts. So VAN is 120 at an angle of 0, VBN is 120 at an angle of minus 120, and VCN at an angle of minus 240. So now we connect these, and there is a neutral here and there is a capital N neutral here. We connect these neutral lines too. So now we can make per phase calculations, and per phase calculations are now easier to make, right? So I'm going to remove all other phases except phase A, right? So now we have removed everything else except phase A to make this per phase calculation, right? So making per phase calculations is easier. Now we have this, a single phase, right? So handling with this single phase is easier, and once we find this phase voltage VAN, we can multiply it with square root of 3, and we can lead it by an angle of 30 to make it the line voltage, right? So given now the circuit is very simple, and we should find this phase voltage, which will then convert into the line voltage, right? To find this VAN, we have to first find the current. Since it's a series circuit, current would be the same throughout. IA would be this VAN 120 at an angle of 0 divided by 0.1 plus J0.2, 12 plus J4, the impedance of the line. So this becomes 12.1 plus J4.2. So when we convert it into a polar number, oh, I'm sorry, there is a small mistake. We shouldn't write it at an angle of 0 because we know that all phase voltages are lagging their line voltages by 30 degrees. So this should be minus 30. We have already studied that when we convert line voltage into phase voltage is lagging by 30 degrees. So we have to put a minus 30 because its corresponding line voltage was 208 at an angle of 0. So this should be minus 30. And if we're going other way around, from phase voltage to line voltage, we lead by 30 degrees. So if we're coming from line voltage to phase voltage, we lag by 30 degrees. So therefore put a minus 30 here. So when we solve, it becomes 120 at an angle of minus 30 over 12.88 at an angle of 19.1. So this number converted into its polar form. So this gives us Ia equal to 9.38 at an angle of minus 49.1 degrees. This much amperes, and all these values are in RMS. It's already given. Right, once we have converted all this, now we are ready to find VAN, this voltage. This is very easy. We'll apply Ohm's law to find VAN. VAN is the current flowing IA multiplied by the impedance ZY, 12 plus J4, and IA is 9.38 at an angle of minus 49.1 times 12 plus J4. So 12 plus J4 can also be written in terms of its polar form. In its polar form, 12.65 at an angle of 18.43 degrees. So if you multiply the two, it comes out to be 118.65 at an angle of minus 30.7 volts. So now we are almost done because we have computed this voltage, which is actually a phase voltage, but we are required to find, I wrote it here, we are required to find the voltage VAB, which is the line voltage. So how do you find the line voltage given this phase voltage? We know that if we are given a phase voltage and we are asked to find its corresponding line voltage, we multiply this value by under root 3, and it is at an angle of minus 30.7. Since we are moving from phase voltage to line voltage, we lead it by 30 degrees. So it's just plus 30 degrees, right? So this is square root of 3 multiplied by 118.5 gives us 205. So this is very important that if we are moving from phase voltage to line voltage, we add 30 degrees. And if we are going vice versa, from line voltage to phase voltage, we subtract 30 degrees, minus 0.7 degree. So this is our required quantity, VAB. Now there is a small homework. Students are required to calculate 4 voltages, VBN, VCN, it's a homework, VBC, the line voltage, and VCA, it's also a line voltage. These two voltages are phase voltages and these two voltages are line voltages. The students have to find these four voltages, right? That's all for this lecture. We'll continue studying three-phase systems. Thank you.